This is Dr. Avdhesh Gupta, Professor in IT Department, and today we will discuss the topic functional dependency and normalization that is related to database management system of third year CSIT students. So, these are some topics we will discuss about it: the functional dependency, different types of functional dependencies, attribute closure, Armstrong axioms, equivalence of functional dependencies, canonical cover, different types of keys. After that, we will start a normalization. Okay. So, what do you mean by functional dependency? Functional dependency, it means one attribute is dependent on another attribute. This can be represented by A tends to B. So, what does it mean? It means that B can be found on the basis of A, or B can be derived. B is a derived attribute on the basis of A. A is the attribute and B is the attribute. The relationship between these attributes is B is functionally dependent on A just because of the value of B can be found on the basis of value of A. Okay. So, let's take an example. Suppose there is a table. The table contains different attributes, different column name. The one column name is like, for example, employee number. Another column name as name, their address, their designation, their email address, etc. So, the other attributes can be found on the basis of employee number. Employee number is the attribute that is uniquely identifiable, and this particular uniquely identifiable column, through this uniquely identifiable column, we can find the other values of that particular row. Okay. So, what does it mean? Email address is functionally dependent on employee number. In the same way, like for example, if we take the roll number and the name of a student, the subjects taken by the students, the teachers taught the particular subjects to the student. So, on the basis of the given roll number, we can find the other related attributes given in the table. Okay. So, we can understand functional dependency by the following two examples. The one example is where the tuples are duplicate, and another example where the tuples are not duplicate, the tuples are unique. So, in this case, these are the duplicate tuples. Okay. So, what in column A? 101 and 101, and the similar way, what is in column B? The Cn and Cn. Okay. So, R is a subset of A. Similarly, R is a subset of B. Okay. So, A and B are the both A and B are the subset of the relation R. So, A and B are the two column name. Okay. So, here we can find that A tends to B, or we can say B is a dependent element or dependent attribute and A is determinant element, or you can say that B can be found on the basis of A. Okay. So, for this example where the tuples are duplicates. So, for this example, if T1 of A, this is T1 and this is T2. So, T1 of A, that is 101, if T1 of A yani ki 101 is equals to tuple 2 of A yani ki 101, both are equal, if in this case, then T1 of B is equals to T2 of B. Okay, just because of, if we are saying that A tends to B and A is common or duplicate, so the value of B should be duplicate. Okay. So, in next case where the value of A is uniquely identifiable, that is not duplicate. So, in this case A tends to B, so we cannot say that tuple of A is equals to tuple of 2 of B A, or any of the tuple is common in this column, or any of the tuple is common in this column. So, we can say that if DBMS can we find on the basis of 102, if 102 is given, so I am saying that subject code is 102. So, you can easily say that 102 belongs to DBMS subject, and 101 subject belongs to CN subject, and 103 subject belongs to DA subject, for example. So, this is functional dependency. Okay. Now, different types of functional dependency. So, to discuss the various types of functional dependency, we take one by one. So, first functional dependency is whether it is trivial or non-trivial. There are two types of functional dependency. In this case, trivial and non-trivial. Another type of functional dependency are also in next slides. So trivial and non-trivial. So we have to find a trivial and non-trivial. The trivial dependency is the trivial dependency. In trivial dependency, the dependency is true, but nothing can be identified, or the particular dependency is not informative. And in non-trivial cases, the dependency is valid, but some new element can be identified. Let's take an example. For example, this one, B subset A and B is not subset of A. ठीक? In this case, AB tends to B, and in this case, AB tends to ABC, just because of this is not a subset. Okay, so this is valid, but not informative, just because of if we cut this B to this B, any new element can be identified on the basis of A? No. So this is not informative. But in this case, AB and AB. So a new element C can be identified. So this is informative and valid. Okay. So this is a non-trivial dependency and this is a trivial dependency. Okay. So this is an example based on the correct functional dependency, whether the functional dependency is correct or not. To understand the functional dependency in better way, this example is best suited. Another two more examples are on basis of functional dependency. So you need to identify which statement is wrong or correct. Okay. So if BC is functionally dependent on A, then this statement will become true. If C is functionally dependent on DE, then this statement is also become true. If DE is functionally dependent on C, then this statement also becomes true. And if A is functionally dependent on BC, then this statement will become also true. So which statement is true among these all four? So let's take one by one. Okay. So A tends to BC. What is the value here in A column? Z and 2. These two values are given. Okay. On the basis of Z, we can find BC 2, 3. On the basis of Z, we can find 2, 3. On the basis of we can find 2, 3. It means 2, 3. Okay. On the basis of 2, we can find Z3. In this case 2, 3, and this case Z3. So this is, I think, in this is true. This is correct. Okay. Let's take another example. DE tends to C. DE. DE is 4, 5, 4, 5 again, 5, 6, and 6, 6. What information you can extract? 3. 3 can be extracted. Let's take. At right hand side only one column, but left hand side different column. So different columns or different tuples can be identified the same. So this can be true. But in this case, C tends to DE. Let's take C. C is 3. C is 3. What do you have identified on the basis of C? DE. It means either 4, 5 or 5, 6 or 6, 6. This is not valid. This is not valid. Just because of right hand side, 3 different attributes can be identified on the basis of C. This is not valid. This is against the functional dependency. So this is not valid. Okay. So this statement will become wrong. Okay. Next, BC tends to A. BC 2, 3, Z3. In this case, if we have given 2, 3, then we can find Z. If we have given Z3, then we can find 2. Okay. So this is very simple. This is also true. So this statement will become wrong. This should be never be happen. Right hand side only one attribute, left hand side it can be more than one. Okay. So on the basis of this also. In the previous example, only one functional dependency you need to check, and in this example, you need to check two dependency at a time. Okay. So you need to identify whether which is wrong or which is correct. But keep in mind that both, and it means both dependency should be true. Okay. So in the first case, xy to z and z to y, xy 1 4, xy 1 5, xy 1 6, xy 3 2, all different. And you have to identify 4, 5, 6, true. Right hand side single column, single attribute, and left hand side also single. So this is true. Xy tends to z. This is true. XYZ to XY. No. Next check Z to Y. Z. Z is 2. On the basis of 2, you can find 4 and 2 also. On the basis of this Z, the 4 can be found and 2 can be found. This is wrong. This is not acceptable in any manner. So this function dependency is wrong, because at right hand side there are two different elements can be found, and this is wrong. So Z tends to Y, this dependency is wrong. Okay. Let's check another. YZ to X, YZ. YZ to X. 4 2, 5 3, 6 3 and 2 2. All are different. Okay. To X, we can find X. Okay. So X 1 1 1. It means on the basis of 4 2 we can find 1. On the basis of 5 3 we can find 1. On the basis of 6 3 we can find 1. 1 1 1. Common. So this is true. This is correct. Correct. But YZ, Y tends to Z. 4 5, 4 2 2, 2 2 2. This is wrong. Okay. Sorry. Let's repeat. This is wrong because of this is. क्योंकि यहाँ पर we can find two different functional dependencies here. Okay. So this is wrong. And YZ to X and Y to Z. Y to Z. It means 4 2, 2 and 2 2, 2. So right hand side, there is no problem right hand side, but left hand side 4 2, it's also true. 3 Y to Z, 5 2 3 and 6 2 3. Okay, there is no problem. There is no problem. But the problem is that 3 3, but left hand side 5 6, and you are saying that XZ is also YZ tends to X. So this is true. Okay, so first is wrong. So in this basis you can find which one is wrong, which one is correct. Okay. So now attribute closure of a set. So this is the next example. This is a new topic, attribute closure. So what do you mean by the closure of an attribute set? The closure is a set of attribute that can be derived on the basis of given functional dependencies. Okay. So we can find the closure of any attribute available in the relation, any attribute. Like for example, if the relation is given ABC or the relation is given R2 ABCDEF, we can find any closure like A closure. Here we can find D closure or DE closure, any closure. Okay. So what is the condition to check closure? The given on the basis of given functional dependency, the new attribute can be derived. On the basis of some determinant attribute. So we need to identify the attributes that can be determined on the basis of given closure. Okay. The symbol of closure is the plus sign. So this is the A closure. Okay. So A closure is what? Just write the attribute, the same attribute name for which you are finding the closure. Like for example, we are finding the A closure, so we should write the A is equals to A. In the next line, on the basis of given functional dependency, if any attribute can be identified on the basis of the available attribute here, on the basis of this attribute, yes, we can find B on the basis of A. So we should write AB here. Okay. So what's now? There are two elements. There are two attributes, A and B. What else? Can we find some other attributes on the basis of independent A or independent B or combined A, B? Yes, we can find C on the basis of B. So A, B, C is the final. No more element can be identified on the basis of given this closure. So this is the final closure. Okay, the closure is very important just because of in the later examples or later when you find the normalization, you need to find the closure. So just to check whether which one is the key for which is the super key, which is the candidate key, and which is the primary key. Just for this purpose, the closure is very important. So here the single attribute, we can find the closure of single attribute and the combined attribute also. Like for example, if we find the let's take in this example, if we find the B closure, so B closure, write B first, then on the basis of B, we can find C. No more element can be identified. So this is the final closure, BC of B closure. Okay. In this, you need to identify the closure of D. So D is written over here. What else? Based on the D, AF can be identified. So AF, ADF. Okay. Next, ADF. Now A tends to B. B can be identified on the basis of A. So AB, DF. What else? Can we find other attributes? C is not there, so we cannot find DE or DE. E is not there, so we cannot find CF. So okay, this is the final closure. Similarly, DE closure. So we should write a DE element. So DE element on right hand side. DE already there. On the basis of DE, can we find another attribute? Yes, we can find DE, D, AF. We can find AF or DE, CF, DE, AF and CF. So we can write along with, right? For example, A, F, C, F is again, so no need to write. A is already there, then D. So in sorting order, we can write that A, D, E. E is already there, D, E. So we can write here A, C, D, E, F. A, C, D, E, F. So A, C, D, E, F. Either you have to do step by step, or you can combine different dependencies at once. Okay. So can another element can be identified on the basis of this one? Yes. A tends to B is also given. B is also identified. So A, B, C, D, E, F. So this is the final closure. No other attributes can be identified on the basis of this DE closure. So DE closure is A, B, C, D, E, F. So this is how we can find the closure. So this closure can be very, very beneficial when you identify, when you find the normalization forms. Okay. So now comes on Armstrong axioms. These are the some rules that there are. You have already read that in discrete mathematics, that reflexive. What do you mean by reflexive rule, augmentation rule, and transitive? So let's repeat it. Reflexive. If y is a subset of x, then x tends to y, or we can say that y is functionally dependent on x. Y can be identified on the basis of x. Okay, this is reflexive. Augmentation, it means something has been added to left hand side and something has been added to the same element has been added to right hand side. Like for example, if x tends to z, then we should write xz to yz. Z is union to x and z is union to y. So z has been added to left hand side and right hand side by union operation. So this is augmentation rule. Transitive dependency. What is transitive dependency? Let's take x tends to y and y tends to z. So can we say that x tends to z? Yes, just because of y. X tends to y and y tends to z. So we can write x tends to z. So this is transitive dependency. This is transitive dependency. Okay. So we can eliminate the middle. We can eliminate the middle element here. On the basis of these three basic, or you can say inference rule, we can find other rules also. Like for example, here we have used union. So this is a rule, union. If x tends to y and x tends to z, so x union x. X both are x na on left hand side, but right hand side is y and z. Then x tends to yz. Y and z are union at right hand side. In the same way, you can say that if x tends to y and z tends to y, then can you write x z tends to y? Can you write x tends to y? X z tends to y. You need to identify this particular issue because this is very important. Okay, next is decomposition. If x tends to z, right, given over here, this particular union and decomposition are vice versa. Like if we added to z element to y, just because of y is functionally dependent on x and z is functionally dependent on x, so we should write this one. X tends to y and x tends to z. This is the decomposition of this union rule. Pseudo-transitivity. What is pseudo-transitivity? Pseudo-transitivity is that x tends to y and wy tends to z. Listen over here. X tends to y. Okay? And this y, something has been added to this y tends to z. Then what will happen? Wx tends to z. This z can be identified on the basis of wx also, just because of this particular y can be replaced by the element of x. Got it? Read it once. Okay, left it. X tends to y, wy. Here is x tends to y. This is wy tends to z. So y can be identified on the basis of x now. So we can say that wx tends to z also. Okay, this is a pseudo-transitivity. Transitive rule, you got it? This is transitive, x tends to y and y tends to z. And the same way, if this happens, then we should write this one. Okay, this is a proof. This is a proof of pseudo-transitivity. Like for example, if x tends to y, then wx tends to wy, augmentation. The w has been added to left hand side on the basis of right hand side. We have already said wy tends to z. So wy is replaced with z. So wx tends to z. wy की जगह z आ गया, then wx tends to z. Okay. Now composition. Composition is what? The same way. This one. Okay. Read it here. If x tends to y and z tends to w, x, y, z, w, both elements are different. All the elements are different. Okay. Then if we combine x and z, then we should combine y and w also. This one. Now listen. X tends to y, then by augmentation rule, zx tends to zy. Z has been added or union to left hand side on the basis of right hand side. And zw, then by augmentation rule, x. Now you need to include x at left hand side and right hand side. Zx and zw, z. Now listen, wx. Now this one. In the same way, x tends to y. So we need to identify zx to zy, z tends to y. So we need to zx X has been included, ZX and XW, WX. Okay. So by combining all unions, or combining all union, ZX tends to ZY X, sorry, this is X, XY, ZW. X, Y, ZW, all these column. ZX, 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 both are common. Both are common. So we should say that ZX tends to WXYZ. This is X. This is union rule. By mistakenly it is written over here. So we can say that ZX or XZ tends to YW. This is decomposition rule. If we break and we apply this decomposition, so we can say that this one. Okay. So now this is some practice on attribute closure or closure of a set of given functional dependency. So solve this. Now, for example, we have to find AC closure. So we should write AC first. Okay. B can be identified. So we should write A, B, C. Okay. BC. From the BC, DE can be identified. DE. So it means A, B, C, D, E. AEG. There is no AEG. So all the elements or the given function dependency can be identified. So AC closure is A, B, C, D, E. This is the final answer. So now you need to identify B closure is equals to B first. Then on the basis of B, D can be identified, BD, and no, nothing else. Nothing else. The BD is the final answer. In this case, AB closure. To write AB first and then AB. AB is equals to A, B, C. A, B, C. Because ABC, C can be identified on the basis of AB. And BC, on the basis of BC, AD can be identified. So is equals to A, B, C, D, because AD. So we should include D element here. A, B, C, D, and E also identified on the basis of E. So it means A, B, C, D, E. So I think A, B, C, D, E. Yes, no other element can be identified. So the final answer is A, B, C, D, E. In this case, you need to identify whether the BCD closure is H or not. Listen carefully that BCD closure, like for example, if I said that AB closure is equals to C, whether this statement is true or wrong, is valid statement. Just because of the C can be identified on the basis of AB closure, which includes ABCD. So this statement can be true or false if we find that BCD closure have the H attribute in this closure. Like for example, BCD, okay, BC, CDE. So B, C, D, E. D, AEH. D hai AEH. You need to write A, B, C, D, E, H. Now H comes. So H is true. This is true. Okay. The last one, AG closure. So you need to write AG first, then A to B, A to C. So A to B, C, G. What else? B to H. So A, B, C, G, H. A, B, C, G, H. CG, CG, H and I. So A, B, C, G, H, I. A, B, C, G, H, I. But D is not here. So A, B, C, H, I. So these are the final answers. Okay? So let's check its answers. A, B, C, D, E. Yes, we can find A, B, C, D, E. BD. Yes, we have find BD. Okay? A, B, C, D, E. Yes, A, B, C, D, E. It is valid. So it is valid. Next, A, B, C, G, H, I. A, B, C, G, H, I. So this is the final. So these are the attribute closure and this is the final slide. So we will get next presentation in the later video. So thank you very much.